These last bit, products to sums, sums to products, not actually in the course as such, but you might find them useful. Certainly in some of the extension 2 questions, it could help you simplify some problems. Might not, you might never use them. But anyway, let's just have a look at them, see what they are. So if you've got a sum, that's a product by the way. If you've got a product of two trig functions, you want to turn it into a sum. What it's basically using is the compound angles, but in reverse. And so they're saying, well, if I've got a sine times a cos, it must have come from the sine compound angle, because I would have gone sine, cos, cos, sine. And I want left A and B, and so when I add them together, the second bit, the cos sine, cancels out. So that's basically where it comes from. So 2 sine A cos B would be sine A plus B plus sine A minus B. Cos must have come from the cosine functions. So if I want that, I'd have to add the two cosine ones together. And then the other possibility, of course, is sine. Also has to come from the cosine function. So it's the one that's a little bit unusual, because you think, oh, well, sine cos comes from sine. But if you think of the formula, it makes sense. Sine would have to come from the cosine function. Difference being, well, I suppose because it's not actually cos, it's sine, that's a bit different. So it's not a plus, it's a minus. That's a bit different. However you choose to remember that, I guess. So if we had to get this product, we've got 2 cos 5x sine x, and we had to express it as the sum of 2. The other place where this could be useful is in integration. And if you had to integrate something like cos 5x sine x, a lot easier to integrate 2 single trig functions rather than one that's multiplied together. So that could be a useful place for this. So cos sine must have come from the sine functions. And so I'm going to rewrite it so it's like I want to see it. So that way I know which one to put first. And that's kind of important because of the a minus b in the second one. So I want the sine first, so I can go x plus 5x and then x minus 5x, because that does make a difference, because the x minus 5x gives me minus 4x. But sine being an odd function, I can rewrite that as sine 6x minus sine 4x. Had I put it the other way around, I would have got 5x minus x, which would have been positive 4x, and I would have left it as plus. So that's why it's important for the sine one, certainly, that they're in the right order. Cosine, not as much of an issue, because cosine is, of course, an even function, so it doesn't really matter. So, but the cos must have came from the cos. Notice here I've only got one of them, so that's why I've said half of. So it's half of the 2 cos. So it must be half of the cos, add them together in the first one, subtract them in the second one. I get minus 2 theta because of the way I've written them this time, but as I say, it doesn't really matter, because cosine being an even function, that would be the same as cos 2 theta. So I want to work out what the 2 sine 45 cos 15. Sine 45, not a problem. That's an exact value, I could do that. But cos 15, I don't know the exact value of that one. But if I turn this into sine plus sine, I end up with 2 exact values, because 45 plus 15 is 60, 45 minus 15 is 30. And so I get sine 60 plus sine 30, root 3 on 2 plus a half, so root 3 plus 1 on 2. Now going back the other way. So sums to products. So if I have sine plus sine, 2 sine half sum cos half diff. 2 sine half sum cos half diff. So look at closely. It's sine plus sine. So I start off going 2 sine. And I'm always going to go half sum half diff. But in the second, so I go 2 sine. So it then must go half sum cos half diff. If it's cosine, then it's 2 cos half sum cos half diff. So both of them end up with cos half diff. It's the first bit that's different. Cos A minus cos B. Well, the minus here, you notice, starts with a minus over here. So it's minus 2 sine half sum sine half diff. Again, it's a bit different because of the minus there instead of the plus. And that's why I've got sines instead of coses. It's a bit different. So let's do some conversions. Cos 3a minus cos 5a. But it's minus, not plus, so it's a bit different. So that's the one that's going to start off minus 2. Sine half sum, sine half diff. But when I look at that one, I've got sine of a minus there, sine being an odd function, so I turn that into 2 sine 4a sine a. Sine minus sine, you notice I didn't have a formula for that one. And that's because before I do this one, I change it to sine plus sine of minus 4x. Basically, I'm going back to the same examples I did before, but doing it in reverse. So when I have sine, I don't bother with the formula for minus. I turn it into a sum by using the feature of odd functions. And then I know it goes 2 sine half sum cos half diff. And there's our 2 sine x cos 5x. Yep. So I want to solve this equation. Sine x plus sine 3x equals 0, which I suppose, okay, I could have expanded out sine 3x, get it all in terms of sine x, and go from there. But if I turn it into a product, because it equals 0, that's going to make it a lot easier, because when we have products equaling 0, we know either one thing equals 0 or the other. So it's sine, so it's 2 sine half sum cos half diff. So I get sine 2x cos negative x, and cos negative x and cos x is the same. So either sine 2x equals 0, cos x equals 0. They're both boundary values we're talking about. The 2x gives me 0, 180, 360, but I'm going around twice. 540, 720, halve those. Cos x equals 0, 90 and 270. I got those answers already anyway, so I don't have to worry. So all of my answers then are just 0, 90, 180, 270, and 360. All right, so let's say, not actually in the course, when they have used it in an exam, or if it's a good idea to use it in the exam, I have noticed that sometimes they actually give you the formula in the exam. But if you